Today in this video lecture, we will see numerical 3 on design of shaft. Numerical is the internal diameter of a steel shaft is 70% of external diameter. The shaft is to transmit 3500 kW at 200 rpm. If the maximum allowable stress in the shaft is 50 MPa, calculate the diameter of the shaft. Also find the maximum twist when it is stressed to maximum permissible value. The length of the shaft is 4 meter. So first write given data of this numerical. Let us assume that capital D as external diameter and small d as internal diameter. And this internal diameter of shaft is small d is 70% of external diameter. 70%, that means 70 upon 100, 0.7 multiplied by capital D external diameter. So this is relation between this small diameter and big diameter, internal diameter and external diameter. And the shaft is to transmit power 3500 kilowatt. And number of revolution capital N is 200 rpm. If the maximum allowable stress in the shaft is 50 MPa, that means this stress tau max 50 MPa, and calculate the diameter of the shaft. Maximum twist and maximum twist when it is stressed to maximum permissible value, and length of shaft is 4 meter. And to find diameter of the shaft, that means small d and capital D, both diameters, and also find the maximum twist when it is stressed to maximum permissible value, theta for when it is stressed to maximum permissible value. Okay, so in this numerical they have given us data. They have given relation between internal diameter and external diameter. They have given power, number of revolutions, and stress, maximum allowable stress in the shaft 50 MPa, and length of that shaft 4 meter. And by using this data, we have to find this diameter and angle of twist. And this is maximum angle of twist when it is stressed to maximum permissible value. So for solving this numerical, methodology is, first we have to use power P is equal to 2 pi nt upon 60 formula, and by using this formula we will find torque. And after this we use polar sectional modulus formula Zp is equal to T by tau, and by using this formula we will find diameter, small diameter, that means internal diameter, and external diameter. And by using torsion formula T by J is equal to G theta by L is equal to tau by R, we will find theta. Theta means angle of twist. So see step by step methodology for solving this numerical. First use P is equal to 2 pi nt upon 60 formula. This P is 3500 into 10 raised to 3. Number of revolution is 200 and T and divided by 60. So this T is 3500 into 10 raised to 3 multiplied by 60 divided by 2 into pi into 200 is 167.112 into only 167,112.69, and this power is in watt, and this number of revolution rpm. So unit is Newton meter. Newton mm. In Newton mm, value of that torque is 169,112.69 into 10 raised to 3 Newton mm. So next step is, by using T is equal to tau multiplied by Zp formula, we get Zp is equal to T by tau. And this Zp for hollow shaft is hollow steel shaft. That means this Zp we had seen in our one of the last lecture. This polar sectional modulus for hollow shaft is pi by 16d multiplied by d raised to 4 minus small d raised to 4. This is T by tau. And this T is 169,112.69 into 10 raised to 3. And this tau is this 50 MP. So pi by 16d multiplied by d raised to 4. This small d is this 0.7 into capital D. Raised to 4. So by solving this equation mathematically in calci, so we get this capital D as 281.88 mm. That means this 281.88 mm diameter required to transmit this 3.00 kilowatt power, and is approximately equal to 282 mm. And by using this external diameter, we will find this internal diameter 0.7 into d. So small d is equal to 0.7 into capital D, 0.7 into, and capital D is 282 mm. $197.4. This is internal diameter 197.4 mm. So we had find internal diameter and external diameter. So our this task is completed. Now we will find this angle of twist. This angle of twist when it is stressed to maximum permissible value. So for solving this angle of twist, solving this theta, we will use tau by r is equal to g theta by L formula. That means torsion formula. T by J is equal to g theta by L is equal to tau by r. And here we don't have this J. See, we don't have this J, polar moment of inertia. And also we had this R, this stress also, this length also, and this shear modulus, we will assume it as 80 GPa. And by using both this relation, we will get this theta. So use g theta by L is equal to tau by R. Why I use this both two relations, this g theta by L and tau by R? Because see this, find the maximum twist when it is stressed to maximum permissible value, and here stress is this and twist is this. So that's why I use this both of these two relations, g theta by L is equal to tau by R, and assume g shear modulus as 80 GPa. That means 80 into 10 raised to 3 MPa, megapascal, gigapascal. So theta is equal to tau L upon gr. And tau is maximum 50. Tau is 50 Newton per mm square or 50 MPa. Length is 4 meter, that means 4000 mm. G is 80 into 10 raised to 3 Newton per mm square or MPa, and radius is 2. See here, radius diameter we get maximum diameter 197.4. No, this is minimum diameter and maximum diameter is 282 mm. So why I choose maximum diameter? Because this angle of twist we have to find maximum. Find the maximum twist, and that's why I use here maximum stress and maximum radius. Radius is diameter divided by 2, that means 282 divided by 2, and this theta is 50 multiplied by 4000, this is 5 divided by 80 into 10 raised to 3 into 282. So 0.0177 radian. This theta value is in radian. See this tau we put in Newton per mm square, L we put in mm, G we put in Newton per mm square, and radius also we put in mm. That means we put here values Newton mm in Newton mm unit, and we get theta in radian. So remember this. And for degree, 0.0177 multiplied by 180 upon pi. Multiply it by 180 upon pi, we get this in degree. So theta is equal to 0.0177 multiplied by 180 upon pi is 1.014 degree. So this is numerical design of shaft. See, they have given us relation between external diameter and internal diameter. They have given power, number of revolution, and maximum stress. Maximum allowable stress for that shaft is 50 MPa, and length of that shaft. And by using this data, we had find diameter and angle of twist. First, we find torque using power formula, and in power formula, we put this power P, this P, and this number of revolutions. So this power P and N, they have provided us for calculation of torque, and torque unit is Newton meter or Newton mm. And next we had find diameter using that polar sectional modulus formula. That means design of shaft formula, strength of shaft formula, T is equal to tau into ZP. So ZP is equal to T upon tau. So this formula we required in this equation, this ZP formula. Remember this ZP formula, and this T we calculated in our step 1, this T. Why we calculated this T? Because this T is required in this step 2 and step 3. Yes. Tau stress they give us in numerical. So this capital DS 282 mm, and this theta angle of twist we had calculated using this torsion formula. So theta is 1.014 degree. Thank you very much.